When you train a large language model, one of the highest stakes decisions is how to split your compute budget between making the model bigger and training it on more tokens. For years, the field has leaned on the Chinchilla scaling law, which famously suggested about 20 tokens per parameter as the sweet spot. But what if the very equation underlying that recommendation is subtly wrong at exactly the scales where you most need it to be right? That is the puzzle this paper tackles. The Chinchilla law says the reducible loss of a language model is the sum of two independent power law terms, one that decays with model size and another that decays with training tokens, plus a constant floor representing irreducible error. Mathematically, this is convenient, but it makes a strong hidden assumption that model size and data volume affect loss independently of each other. If you take the mixed partial derivative of loss with respect to both variables, an additive form forces it to be exactly zero. In plain terms, the additive form insists that adding more parameters gives you the same marginal benefit no matter how much data you have, and vice versa. The authors argue this is empirically false, and the failure shows up as a saddle-shaped pattern of errors. Chinchilla systematically overestimates loss in some corners of the size versus data grid and underestimates it in others, with errors reaching several percent right where you'd want to extrapolate to frontier scale. Before proposing a fix, the authors do something refreshing. They interrogate the loss surface directly using a technique called moving least squares, which fits local polynomials to estimate derivatives from noisy data on a grid. Think of it like using a flexible ruler to measure the slope of a hillside at many points, rather than assuming the hill has a specific shape. When they estimate the mixed second derivative of loss with respect to model size and tokens, they find it is decidedly not zero. It is consistently negative and follows its own power law decay. That negative sign is meaningful. It says scaling model size and data together reduces loss more than the sum of scaling each alone. There is genuine synergy between capacity and data, and any additive law is architecturally blind to it. Enter the scaling law, which is the paper's central contribution and, honestly, a beautifully minimal fix. Instead of adding the two power law terms and calling it a day, the authors sum them inside parentheses and raise the whole thing to a single new exponent called k. When k equals 1, you recover Chinchilla exactly. When k differs from 1, you get a coupling between model size and data that produces a non-zero mixed derivative, exactly the interaction the empirical surface demands. This threads a needle between the original Kaplan formulation, which coupled the two variables but tied their inner exponents together, and Chinchilla, which decoupled them entirely. Scaling keeps independent inner exponents like Chinchilla, but adds one outer exponent that governs how the two contributions blend. The whole method adds exactly one parameter to the fit. It's the scaling law equivalent of realizing your recipe needs a pinch of one specific spice, not a whole rewrite. There are some elegant properties baked in. Because k stays positive, loss remains monotonically decreasing in both dimensions, so you never predict that adding data or parameters somehow hurts. And because the outer exponent factors out cleanly, the compute optimal allocation still has a closed-form solution, which means practitioners keep the same convenient recipe for choosing model size given a budget, just with different fitted numbers underneath. The second big idea is a sparse sampling strategy called L-shape profiling. Normally, to fit a scaling law, you train a dense grid of models across many sizes and token counts, and the compute is dominated by the largest, longest runs in the top right corner of the grid. That's incredibly wasteful. The authors observe that in the asymptotic limits, one axis cleanly isolates the other's parameters. As data goes to infinity, loss depends only on model size parameters, and vice versa. So they train only along two cheap edges. One strip sweeping data volume at the smallest model sizes, and one strip sweeping model size at the shortest training horizons. Together, these form an L shape hugging the low compute corner. Picture surveying a mountain range by walking only its foothills along two perpendicular ridges rather than climbing every peak. Because scaling's coupled form is anchored by asymptotic edge behavior, the L shape provides enough signal to recover the full surface. The experimental results are striking. On the FARSEER dataset of 404 pre-training runs and their own SK grid of 134 runs, Skaling reduces mean absolute percentage error by roughly 1.5 to 3 times compared to Chinchilla across interpolation and extrapolation regimes. The most dramatic gains appear in the far extrapolation corner, where models are simultaneously larger and trained longer than anything in the fitting set. On SK Grid Full Grid, far extrapolation error drops from 5.17% to 0.70%. On the L-shape variant with roughly 10 times less compute, Skaling still beats full grid Chinchilla in most settings, and far extrapolation error stays around 1.15% versus Chinchilla's 14.63% under the same sparse regime. The fitted coupling exponent lands consistently around 0.31 to 0.45, well below 1, confirming that the data genuinely wants a coupled form. Notably, the more heavily parameterized 9-parameter FARSEER law does not match Skaling despite its extra flexibility, suggesting that inductive bias matters more than raw parameter count. There are some caveats worth surfacing. The paper notes an identifiability issue. The coupling exponent K and the irreducible loss floor E trade off against each other because none of the runs reach true saturation. Skaling tends to push the floor down close to 0 on some datasets, which the authors are careful to say does not mean loss actually goes to 0, just that the fit resolves the ambiguity in a particular direction. Also, the benefit weakens when the underlying data really is close to additive, which they observe on code training data where Ka drifts back toward 1. And the direction of the compute optimal allocation shift depends on which dataset is fit. So Skaling changes large-scale allocation prescriptions, but the sign of that change is not universal. That's an important warning for anyone hoping this paper gives them a single new magic ratio. Now let's walk through some questions you might have after hearing all of this. First, why does one extra parameter make such a big difference when a 9-parameter alternative like FARSEER doesn't beat it? The answer comes down to inductive bias. The FARSEER law adds flexibility by letting the dataside exponent depend on model size in complicated ways. But that flexibility is somewhat unconstrained and hard to fit stably. Skaling's single outer exponent is a surgical intervention that directly encodes the specific structural fact the data demands, namely a non-zero mixed derivative between model size and data. Adding parameters helps only when they encode the right structure, and one well-placed parameter can beat many loosely constrained ones. Second, how does the L-shaped strategy avoid throwing away critical information? Doesn't the interior of the grid matter? Here's the intuition. The coupled functional form is largely determined by the behavior of loss along each axis in isolation. The data-only sweep at small models pins down the data-side power law, and the model-only sweep at low token counts pins down the size-side power law. The coupling exponent K then just tells you how these two behaviors blend when both are varied together, and you don't need to densely sample the joint space to fit that single scalar. It's a bit like how you can reconstruct a smooth surface if you know its behavior along 2 boundary curves, plus 1 blending parameter. Third, if scaling changes the optimal token-to-parameter ratio significantly, why haven't we noticed this before at frontier scale? The paper's analysis on FARSEER data suggests the optimal ratio actually drifts downward with compute, whereas Chinchilla predicts it stays roughly flat. The reason this discrepancy is easy to miss is that at any single compute scale, both laws can fit the data reasonably well. The divergence only appears when you extrapolate far. Frontier labs typically pick a fixed ratio based on Chinchilla-style guidance and then commit to massive runs, so they never get feedback about whether a different ratio would have been better. This is exactly why more accurate extrapolation from cheap experiments matters so much. For large-scale recommendation systems serving billions of users, the practical implications are quite direct. Recommendation platforms increasingly train large embedding-based models and sequence models with their own compute versus data trade-offs, and teams routinely run scaling studies to decide how to allocate GPU budgets between bigger user and item towers and longer training on more interaction data. If the underlying scaling law systematically miscalibrates at the boundaries, then the token-to-parameter analog for these systems, which might be interactions per embedding dimension, could be off by an order of magnitude, leading to real wasted compute at production scale. Adopting a coupled functional form like scaling for internal scaling studies could sharpen these decisions substantially. The L-shaped sampling strategy is arguably even more valuable in recommendation contexts, where retraining even medium-sized models on production-scale interaction logs is expensive, and where teams often need to justify capacity investments to leadership. Instead of running a dense grid of ablations, a team could sweep only along the two cheap edges, small models with lots of data and large models with brief training, and recover reliable predictions about how a fully scaled candidate retrieval or ranking model would perform. That reduces the experimentation case by roughly 10 times, while giving product managers and infrastructure teams defensible forecasts before they commit to a multi-week production training run.